incompressible fluid, mean rho constant, we can take out all the rho, put it aside. Okay? Fluid flowing on the x direction, which means we are talking about that direction only. But even with that direction, you can see that x component, the velocity can have a variation in x, in y, and in z. Okay? If you don't believe, like this. Imagine myself and my hand is two different entities. Imagine, right? Imagine my hand and myself is three different entities. Now when I move like this, okay, my body maybe move faster than my hand, so it will deflect like that, right? Or the hand move faster than my body, which means the velocity, even though it is on the same direction, right? It is u, right? The u component, only in the x component. But u is a function of, this direction is y or z. You can see now that u is function of z also, right? The hand can be faster than this one. Now we are talking about this. Same goes for this one, right? It can deflect like that, it can do like that. Okay? That is in z direction. How about in x direction? How can you have a different x? Okay, you see my u here is 1 step per second. Suddenly in here, due to something, it becomes 2 steps per second. Right? That one is a function of x. So you can see, even though phi and w is 0, but u is not only a function of x. It can be a function of z, y. Luckily, it is not a function of time, right? Because steady flow. Otherwise, my speed here 1 second ago will be different with my speed here 2 seconds later. Right? Even though you are in the same location, now and later you have a different. Okay? Luckily you have infinite plate. Okay? Because you have infinite plate, there is no effect of side wall. What happens if you have a side wall? Viscous will take place, right? If you have a side wall, let's say my hand is different entity. When it touches the wall, it will tend to stop and it will do that, right? But because the side wall effect is not there, now my hand can move happily with me together. We march together. So in this case, the u is not a function of z because of the infinite length. Clear? Okay, so that's happened because you don't have the side wall. Okay, so now u is not a function of z, so u is only a function of x and y. We will keep that. Gravity working on negative y direction, and it is viscous fluid. Now let's take a look at our conservation of mass. Okay, bear with me 5 more minutes because we are dealing with the steady state. Okay, because we are dealing with steady state, 0 dt is equal to 0, right? All these ut is equal to 0 because we are talking about steady state. So everything involved time has to be 0. Next, you know that phi and w is equal to 0. So anything that have phi and u will become 0. So you end up having du dx is equal to 0. When du dx is equal to 0, you know that u will be 0. Not necessarily. To 4. Become? Is u 0? Not necessarily. So, If you do that, U is constant. What happens when U is constant in the x direction? Mean it is not a function of x, which means if I am the particle of fluid, my velocity here in the x direction will always be constant. Clear?
Yes, sir.
Now, which means the U is only a function of y. Right? The only difference is those. Okay? So near the wall, the velocity may be different. In the middle of the space between the plate, the velocity may be different. So it's only a function of y. Now, because we have that, if we apply to the momentum equation, you know that u is not a function of x. So whenever you have du dx, it becomes 0. Du dx becomes 0. But this one is du dy. Why it becomes 0? Because of phi. Phi is equal to 0. How about this one? This one? If du dx is 0, the derivation of 0 is equal to? 0. You know why this one 0? The whole chunk is 0 because it is 0. Because it is in incompressible flow. Okay, ladies and gentlemen. Okay, so when you do that, if you do that, you will end up scratching almost everything but that one, this one, and that one. So, okay, boys and girls, after you do all these, finally you will end up having a very nicely presented equation. This one only. Okay, so from this one you end up having this one. Okay, but I'm sure this one still not make you happy because it still have those things, right? But since u is a function of y only, so you can change the partial derivation into the ordinary differential equation, which means it changed from PDE into ODE. What is PDE, ODE? Ask your lecturer. Dr. Mohana maybe, or maybe Dr. Chandra. Not mine. Okay? So you do that, you will end up having this and those. When you integrate, you will have this one and you'll have that one. If you realize this one is your y is your. You still remember your static, fluid static? This one is your now, right? If the fluid is not moving, okay? If the fluid is not moving, this one becomes 0. So you will know that only this one is there, because then dp dx is equal to 0, dp dz is equal to 0. So the only pressure working is the hydrostatic pressure working on the y direction. So now you know that Navier Stokes is very powerful. It can be used for both fluid flowing and fluid at static condition. Now you see the relation. Okay? Because this F1x can be P1 or the atmospheric pressure. Y is the distance between P2 and P1. Okay, I think my time is almost end. So please try to solve this one. So if you do double integration for this one, you double integrate it, it becomes this one. Okay? And this, if you implement the boundary condition, it will be